Okay, so this is a follow-up to the very brief introduction to solubility. So I have displayed for you a question from 2010. This is 2010 version A, solubility product, constant stuff. So I'm going to go through this very quickly, just to kind of give you an idea of how it works. I'll try and squeeze in the answers as best I can in the margins, and then we'll go from there. So at the top you see this reaction is carried, several reactions are carried out with the silver bromide, which is cream colored, and it has a KSP value of 5 times 10 to the negative 13th. It says write the expression for the solubility constant, so you can show this, and that'll get you a 1 point. Pretty basic stuff. Question B, calculate the value of silver ions in 50 mils of a saturated solution of silver bromide. Now this is somewhat of a trick question because it wants the concentration of silver ions present. So in other words, you're going to find X in that ice technique stuff that we learned. So quickly remember that we define the solubility, let X equal the solubility of silver bromide, and then we substitute into our ice technique, and because these are coefficients of 1, this is the ice technique, then at equilibrium it's going to be X squared, the product of those two, is equal to KSP, and X equals the concentration of silver ions from above. So if we do a little bit of calculation, it's approximately equal to 7.1 times 10 to the negative 7th moles per liter. The 50 mils is there to throw you off. It's 7.1 times 10 to the negative 7th moles per liter. So that ratio is fixed. Whether it's 50 mils or whatever, that's the ratio. If they asked you specifically for the moles present, then you could convert using this as a conversion factor. Let me clear a little bit of room here. Going on to part C, you can see that you have a 50 mil sample of water is added to the solution in part B, so that is enough. That clue there, we're going to have 100 mils total, so just in case we need that. And it says some solid AgBr is at the bottom. The solution is stirred and equilibrium is reestablished. Some solid silver bromide remains in the beaker, meaning that it's again reached equilibrium, it's saturated. Is the value of silver greater than, less than, or equal to? Well, the silver, it's the same. It's exactly the same as before. The volume of the solution does not determine the concentration at equilibrium. The ratio of moles per liter is exactly the same. So volume does not in any way determine the molar concentration. Okay, so the answer is equal. For part D, calculate the minimum volume of distilled water in liters necessary to completely dissolve a 5-gram sample of silver bromide at 298 Kelvin. And they do give us an approximate molar mass. Okay, this is a little more challenging, but still, it's based upon previous information. The minimum volume of distilled water in liters necessary to completely dissolve it. Well, we do know from a previous problem that the solubility is 7.1 times 10 to the negative 7th moles per liter. We know that for a fact. And so the minimum necessary would be enough so that the number of moles present here in 5 grams divided by the whatever that missing volume we have is be equal to, just equal to 7.1 times 10 to the negative 7th. Or in other words, we can set the solubility equal to the number of moles, which is 5 grams, very approximate values, divided by the molar mass. So there's the moles of silver bromide and the missing volume there. So at this ratio, this is the cutoff point. Okay, this ratio would be the cutoff point for solubility. At volumes more than this, greater than this, this quotient gets smaller than that value, and we're not at equilibrium, and therefore we're below the value. So it's not, there's no precipitate. And then above that value, obviously we'd have, below that value, lesser volumes would be more concentrated, and a precipitate would form. So I'm just going to go ahead and solve for X, and we get a value. It's a fairly large value. 3.7 times 10 to the 4th liters. So that's the volume we get solving this expression. It's a lot of water. So obviously we need it's not very soluble, which makes sense. The K value, or the solubility, is very low. The KSP is very low, meaning we need a lot of water. We need to really dilute this sample. Going on to part E, we see that a student mixes 10 mils of 1.5 10 mils of 1.5 times 10 to the negative fourth molar and 2 mils of this, and stirs it. What will the student observe? Okay, well, this is an issue of precipitation. So we're going to determine the moles of silver, the moles of bromide, the sodium and nitrate are spectators, and we're going to determine if the product of their concentrations is equal to, less than, or greater than K, and make a judgment. So 0.01 liters times 1.5 times 10 to the negative fourth molar will give me the concentration of silver ions. Excuse me, the moles of silver ions. I'll do 0.002 liters times 5 times 10 to the negative fourth molar. This is for the bromide, excuse me. And then once I have those numbers, I would divide them by the total volume, which is 12 mils, or 0.012 liters, which would give me the molarity of each, which would be substituted into the KSP expression. So I'm going to kind of skip ahead to save us a little bit of time, but if you go through those numbers, you get the following values here. I'll write them in red for you so you can see them. We get, hope I can read my own writing on my notes here, 1.25 times 10 to the negative fourth, and here we get 8.3 times 10 to the negative fifth. Now substituting into the K expression, the K expression is that KSP equals 5.0 times 10 to the negative 13th, and that's going to be equal to the product of these two, 1.25 times 10 to the negative fourth, both to the first power. Now, I guess I should have done it without the K value. We multiply these two, and we get a K expression, a value of 1.04 times 10 to the negative 8th. Now remember, that's Q, that's the current conditions. Please see that this value, Q, is larger than K, meaning there are too many products. The reaction will shift to the left and a precipitate will form. Okay, it's important to understand. Q is larger than K, will shift to the left, and a precipitate will form. Moving on to part F. The color of another salt of silver is yellow. So silver iodide is yellow. Student adds sodium iodide to the test tube, containing a small amount of solid cream-colored AgBr, meaning a saturated solution. After stirring the contents of the test tube, the student observes that the solid in the test tube changes from cream to yellow. In other words, the silver bromide goes away, replaced by silver iodide. Write the chemical equation for this reaction. Well, the silver bromide that is present is reacting with the iodide ions. The sodium is a spectator, to form solid silver iodide and releasing the bromide ions. So there's the balanced equation. Which has the greater KSP value? So remember in the intro, the larger the K value, the more products are favored. Or the lower the K value, the less products are favored. Another way of thinking about it is the higher the K value, the less likely the products are to reform the insoluble compound. So if we see here that if we do some reasoning here, you see that silver iodide is more likely to form. In other words, the reverse of this reaction, this direction, is more likely to occur. That's what this reasoning tells us. Telling us that that K value is a very small number. Okay, that they would more likely, they prefer to stay in the solid form. So from that reasoning, the K value of silver iodide must be a smaller number because it has a greater tendency to form the solute. So the answer is the greater K value is AgBr. It's more likely to be soluble than the AgI. Just we conclude that from the color change in this problem.